Hi, my name is Bahadur Akhmedov. In this video lecture, we are going to discuss about the null spaces. We're essentially define null space and we're going to talk about something which is called a spatial solution. So if you are given a matrix A, there are two important spaces about this matrix A. So one is going to be called as the column space of this matrix A, and another one is going to be called as the null space of this matrix A. So previously we talked about the column space and we defined this as the all possible linear combinations of the columns of the A. But essentially, both of the spaces are about the system of linear equations. So if you are given a system of linear equations AX is equal to the B, all possible vectors which you can create using this matrix A is going to be the column space. Or essentially, if you're given a matrix A, all possible vectors AX makes the column space or fills the column space of this matrix A. So at the same time, now it is time to define the null space. So we say that the null space is all possible vectors X, which makes the multiplication of the A to the X to be equal to the 0. Or it's a 0 vector, by the way. And again, so the null space of this matrix A is going to be all possible vectors X, so that the AX is going to be equal to the 0. Okay? So you see, so in order to find the null space, you need to find all of the solutions for the system. So this kind of system, when the right-hand side part is equal to the 0, is going to be called as the homogeneous system of linear equations. So essentially, we talked about the homogeneous system of linear equations before. Whenever you're given a homogeneous system of linear equations, you can always find the solution, right? So let us consider two examples of the homogeneous system of linear equations to show you that, hey, the solution exists always. So let's start from the first one. So example of the homogeneous system of linear equations. So let's say you're given a matrix 1, 2, 3, and 4. Okay, so I would like to figure out here the two numbers so that the linear combinations of this vector and this vector is going to be simply 0 and 0. Okay, so the first solution which comes to your mind is probably 0 and 0. Okay, so essentially, if you multiply this matrix to this vector, and you can multiply this as the linear combinations of the columns of this matrix, so this is going to be 1, 3 times to the 0, plus 2 and 4 times to the 0, right? This gives you this vector, 0 and 0. So, well, obviously, if you are given the AX is equal to the 0, you're going to always have the solution, which is going to be a 0 solution. Well, sometimes we're going to have a non-zero solutions, but in that case, the matrix A should have dependent columns. So essentially, when I say is dependent columns, is that you can obtain one of the columns by just multiplying the first one to some constant. So here, these two columns of this matrix A are independent. So what does it mean? It means that you cannot really get the second column by just multiplying the first column to the constant. Okay, so that is why there's only one solution, x is equal to the 0, and we call the solution, x is equal to the 0 solution, as the trivial solution for the homogeneous system of linear equations. But now let's consider a situation when you're going to have a non-trivial solution as well. So let's consider an example. So let's say you've got the matrix with the entries 1, 2, 2, and 4. Okay, so I say that, hey, could you please give me now a non-zero solution which makes this multiplication to be equal to the 0 and 0. So essentially, I'm looking for such a vector x or x bar which makes this multiplication to be equal to the 0, right? So if you look to these two columns, they are kind of dependent, right? because you can obtain the second column here by just multiplying the first column to the 2. So essentially, if you multiply 1 and 2 to the 2, you're going to get 2 and 4, which is going to be the second column, right? So essentially, they are dependent. And is it possible to get the 0, 0 from this equation? Yes, if I just put this second column into the left-hand side, what I will get is essentially 2 times to the 1 and 2 minus 2 and 4. Well, let me write this as a minus 1, right? 2 and 4. And this is equal to the 0 and 0, right? So what we need to do is we just need to get this 2 and minus 1 and put them as the entries of this vector. So essentially, it's going to be 2 and minus 1. And if you multiply this matrix now to this column, you're going to get exactly 0 and 0. So this is the non-trivial solution for the homogeneous system of linear equations. And if the homogeneous system of linear equations has the non-trivial solution, then it is going to have infinitely many solutions. Why is that? It is because you can just multiply this vector to any constant, and it's going to be still a solution. So do you want to multiply this, for example, to the 2, right? So this is going to be minus 2 and 4 vector. And if you multiply this as a 1, 2, 2, and 4, it is going to be, this 4 is going to be multiplied as the first column, was the entries 1 and 2. Minus 2 is going to be multiplied as the second column, was the entries 2 and 4. And if you add them, you're going to get 0 and 0. So you see, so if there is a non-trivial solution, then the system of linear equations, a homogeneous system of linear equations, is going to have the infinitely many solutions. So by the way, 0, 0 vector is also going to be the solution here, right? So you see, so no matter whether the columns of the matrix are independent or the columns of the matrix are dependent, so this solution, x is equal to the 0 solution, exists in both of the cases, right? So it exists here and it exists here. So which brings me to the natural question, whether the null space is the vector subspace or not. And it appears, yes, it is a vector subspace. It contains this 0 vector, right? If you remember, the necessary condition to be a vector subspace was that your vector subspace should contain the 0 vector, right? And the two more conditions is that any linear combination should be again in the vector subspace. So let's write down the definition. So the definition of the null space. And again, let your matrix A is given as the n by m, for example. Then, so the null space of the matrix A is going to be all possible vectors, which are going to be m by 1 vectors. So all possible m by 1 vectors, right? So that A times the x is going to be the 0 vector. So this is the definition of the null space. And the null space is the vector subspace. So how we can check this? So what we want is we would like to get any two vectors from the null space of this matrix A. Okay, so let's take y and z is from the null space of this matrix A. Okay, so let us denote this was the n of A. And what does it mean that this y and z are from the null space? It means that if you multiply the A to the y, this is going to be the 0 vector. And if you multiply A to the z, it is also going to be equal to the 0. So essentially, any vector from the null space of this matrix A should make this multiplication to be equal to the 0. So now, do you remember the two conditions should be fulfilled to be a vector subspace? Was that the summation of any two vectors should be equal to the 0, right? Which is true in this case, right? So you take any two vectors from the null space, and we can check. So they are making this multiplication ax is equal to the 0. So it's in this case, AY is equal to the 0, AZ is equal to the 0. And now I would like to check whether A times the summation of these two vectors is equal to the 0 or not. And obviously it is 0 because I can just open the brackets. It's going to be AZ plus AY, which is going to be 0 vector plus the 0 vector is equal to the 0 vector. Okay, well, this vector is also Z plus Y is also from the null space of the matrix A. And the second condition is that if you multiply the Y vector to any constant, it should be also from the null space. And the way how to check this, to just multiply this vector to the matrix A and check whether this is equal to the 0 or not. Obviously it is 0, right? So since the K is a constant, I can write down this is a constant times the Y, AY. So since the AY is equal to the 0 because the Y is from the null space, right? Then it becomes K times the 0, which is equal to the 0 vector. And again, K times the Y is also going to be from the null space. So you see, so the null space is the valid vector subspace. So let's do an example when we need to describe the null space of a matrix. So let's do an example. So let's say you are given a matrix A with the entries 1, 3, 2, and 6. Okay? So what I want is I would like to describe the null space. So what does it mean? It means that I need to get this matrix 1, 3, 2, 6. I have to multiply this to the vector x1 and x2, and this should be equal to the 0 and 0. Okay? So basically, I need to solve the system of linear equations, and the way to solve this would be to use the Gauss-Jordan elimination. And if you remember in the Gauss-Jordan elimination, you took the coefficient matrix and you took the right-hand side part, right? And put them together in the augmented matrix. So let's do this together. So it's going to be 1, 2, 0, 3, 6, 0. So the first thing which we need to get rid of is this 3, and we can do this by multiplying the first row to the minus 3, and adding this to the second will lead to the elimination of the 3. So let's do this together. It's going to be 1, 2, 0, 0, 0, 0. So there are two observations of me in the situation. The one observation is that, hey, so I just put the 0, the right-hand side part 0 to here as the last column of the augmented matrix. And this column is not changing, right? It means that if you're given a homogeneous system of linear equations in the form of AX is equal to the 0, the augmented matrix may contain only the coefficient matrix. I don't need this right-hand side 0 vector because it doesn't change it. It's going to be always 0, right? So now the second condition is that, so the null space is going to be all the solutions for the system as well, right? And if you write down the first column of the system, you're going to get x1 plus 2x2 is equal to the 0. And if you remember, this is an equation of a line, right? So the equation of the line was ax plus by is equal to the c, which is very similar to this one, right? So you're multiplying a constant as a variable plus another constant as a variable, and this should be equal to the third constant from the right-hand side part. So this is the line, and we say that the null space of this matrix A is all vectors along this line. The problem is, so defining the null space by just describing this line is not so it's not so cool. So it's not so elegant in terms of mathematics. And what we want is we would like to describe the null space as the parametric equation. In order to do this, we're going to introduce so-called spatial solutions. The spatial solutions. Okay. So again, I would like to write down the system. So the x1 plus 2x2 is equal to the 0. So you see, so if you've got just one equation and two variables, it means that one of the variables is simply the free to choose, okay? So let's assume that this is going to be the second variable. So this variable is going to be the free variable because I can freely choose its values, okay? And the value which is going to depend on the values of the xt is going to be called as the pivot variable. Pivot variable. And again, so it is the dependent variable because it is going to depend on the values of the xt. And xt, which is the free variable, is going to be called as the independent variable. So what I want is I would like to assign a parameter, and we are going to always assign the parameters instead of the free variables or independent variables. So we said that xt is going to be equal to the t, and I'm going to just substitute this to here in order to get the equation, which is like x1 is equal to the minus t xt, or just simply minus t t. Okay? Then again, if I would like to write down the solution vector as the components x1 and xt, this is going to be equal to t and minus 2t. So we can take out the t from the brackets. It's going to be 1 and minus 2 times to the t, right? So this is going to be the x bar. And you see, so I wrote down the same line in the parametric equation. And we call this as the null space. So all of the null spaces is going to be all of the vectors which are obtained in this way for all values of the t from the set of real numbers. So this is how we are going to describe the null space. So now what I want is I would like to describe the null space for the larger matrices. So let's say you are given a matrix. Okay, so this is how we are going to define the null spaces of the matrices. So you see, so the solution which we obtained here, so this solution which we obtained here is going to be called the spatial solution. So later on in our next video lectures, you will see that so the number of the spatial solutions is going to be dependent on the number of the free variables. So essentially, if there is one free variable, then there is going to be one spatial solution. If there are two free variables, there is going to be the two spatial solutions. So essentially, the number of free variables is equal to the number of spatial solutions. Spatial solutions. And what we are going to define is the null space of this matrix A is the span of all of the spatial solutions. And if you remember, the span means all linear combinations of the spatial solutions. Well, in our next video lectures, we're going to discuss about the spatial solutions in more details and try to figure out how they're connected with the parametric equations. So thank you very much for your attention. I hope that this video was helpful for you.